All right, so the second example is so-called Lebesgue measure. Measure mu uh, is defined on Borel sets of r to the power, let's say d, as follows. Uh, for subsets of this type, A1, B1, let's say, AD, BD, product of intervals. So it's a, rectangular box. Okay. A measure of this is defined to be the product of the lengths of the sides. Okay. AI, BI. Uh, okay. Uh, so for example, D equals 1. This is just, the measure which gives us the lengths of intervals, right? For D equals 2, so on R2, so here, AB is an interval, and its measure is just the length of the interval. But if you have, let's say, a rectangular box in R2, then its measure is the area. So this is B minus A times D minus C. Okay, so let's say AB, CD. So we have a box like this, and it's the area of this box. Okay, so this is the Borel, Lebesgue measure, and clearly this measure is sigma finite but not finite, right? Note that, mu is not finite. However, uh, it is sigma finite. Why is that? Uh, well, you can write r to the power d is the union of this kind of intervals, right? Let's say minus n uh, times minus n uh, n from 1 to infinity. I just take boxes of side lengths, well, 2 n's, and then I let n go to infinity. Here, the measure of each, let's say this is an, okay, each an, what is the measure of this? Each side has length 2n, and I have these sides, so the total measure is just 2 times n to the power d, and r d, so the whole space is the union of these elements, right? It's a countable union, therefore our measure space is sigma finite, not finite but sigma finite. Okay, total measure is infinite, nevertheless it is sigma finite. Any questions so far? Okay, now here is another definition. Okay, let omega A be a measurable space So omega is a non-empty set and A is a sigma algebra on sigma. Okay. A measure, let's say P, defined on the sigma algebra, A of events, right? Elements of the sigma algebra are also called events. So it's defined on the algebra and takes values in the real numbers. This time we exclude infinite, satisfying the following uh, condition. So the total measure is 1. So it's a finite measure space. Is called a probability space, or sorry, measure. Probability measure. Uh, so if a measure has total mass 1, then we call it a probability measure. Okay. In particular, a probability measure P, so it's a measure defined on a sigma algebra, is characterized by the axioms. What are they? Well, two of them are the axioms of the actually measure. So the P1, okay, P1 is this. Total measure or total mass is 1. And of course, any measure satisfies this. The measure of the empty set is 0. Second one, any event or measurable set has non-negative measure. Non-negative measure. And the final one is if AI, I is in an index set I, is a countable family of mutually exclusive events, pairwise disjoint sets, yani pairwise disjoint sets in the algebra, then the measure of the union, right, is the sum of the measures. PAI. Okay. So a probability measure is just the measure whose total mass or measure is equal to 1. Okay. Here is an example. We have seen already some examples. Well, they were not probability measure because none of them had total mass 1. This is a probability measure. So let omega be a set and A the family family of all subsets of A, of omega. So the power set of omega, the biggest sigma algebra on omega, fix some element of the omega, set omega, and define the following function or measure, delta omega A. It is defined this way. It is 1 if omega belongs to A, 0 otherwise. Okay. So your sigma algebra is the power set of omega, and you define this measure on this sigma algebra. You take any subset of omega. If it contains this fixed element, you choose some element omega, you fix it once for all. If your subset contains this element, the measure of this subset is 1. Otherwise, it is 0. Well, this function satisfies all these three properties. Why is that? Well, measure of omega is 1 because omega contains omega. The measure of empty set is 0 because empty set doesn't contain omega. So by definition, the measure of the empty set is 0. And if you have disjoint union of countable sets, then the measure of that will be what? If one of them contains omega, then the union will contain omega, and only one of those subsets will contain omega because they are pairwise disjoint. Therefore, the measure of the union will be 1, and the sum of the measures of the subsets will be 1 because one of them will be 1 and all the others will be 0. So if you add all these numbers, you will end up with 1. And if omega doesn't belong to any of the AIs, then the union will not contain omega. Therefore, both sides will have measure 0. Okay, so clearly delta omega is a probability measure on A called the Dirac measure. Dirac measure concentrated on omega. Okay. I guess it is clear why it is called this way, right? Peki. Okay, remark. Note that a probability measure P on a sigma algebra okay, sigma algebra omega A satisfies the followings. Bir kısmını gördük ama şöyle bir liste olarak yapalım. We have seen some of these already. If A and B are two elements, then and so if A is contained in B, then the measure of B is less than the measure of no, measure of A is less than the measure of B. Second one, if A is an event, then P of A is less than P of omega, because omega is bigger than A. It contains A, and this is of course equal to 1 by the assumption. So measure of any event is less than or equal to 1. If A is an event, then its complement is also an event. And what is the measure of that? Well, this is of course measure of A uh, and measure of A complement minus measure of A, and this is just, since these are disjoint, this is the measure of the sum, union, and this is just omega. A union A complement is omega, and the measure of omega is just 1. Therefore, we have this. So measure of the complement is just 1 minus the measure of A. Okay. The fourth one, well, we already know this. Okay. Yeah. If we have two subsets not necessarily disjoint, then the measure of the union is what? Well, this union can be written like this, right? This is just uh, okay. Yeah, this is, I guess this can be written like this. A union B minus A, and this is a disjoint union, right? Disjoint union. So this is just A plus measure of B minus A. Uh, okay, and measure of B minus A can be written as what? This is the measure of B. So measure of B minus the measure of A intersection B. Right? Why is that? Because B is the disjoint union, since B is the disjoint union of uh, B minus A and A intersection B. Right? Uh, is a disjoint union. So since this is a disjoint union, the measure of B is the sum of the measures. Therefore, the measure of B minus A is just the measure of B minus the measure of the intersection. Okay, so that's why we can write this. So measure of the union is the sum of the measures of the subsets A and B minus the intersection of A and B, the measure of the intersection. Tamam mı? Any questions? Well, by induction, one can prove also the following. Okay, so if A1 up to AN are elements of the sigma algebra, then the measure of the union A1 up to AN will be what? This will be the following. Sum of the measures of each AK minus sum of the intersections of the pairwise intersections. So here you have to be careful. You subtract the measures of the intersections, but then when you take out this intersections, you actually take out triple intersections more than once. Therefore, you have to add them back. Okay, so that's what you do here in the summation K1, K2, K3, and here you add all these K1, K2, K3, and you keep doing this. Okay, you keep doing this till the intersection of all of them. So P A1 AN. And what will be the sign here? So you see, if you have intersections of two elements, then it is minus. If it is intersection of three elements, it is plus. So it goes plus minus like this. So if you have n of those, it will be n minus 1. So if n is even, n minus 1 will be odd. So it will be a minus. Otherwise, it will be a plus. So using induction, you can prove this. I guess these properties are, trivial when you, for example, consider the counting measure, right? You have a set, you have subsets, and you count the elements of the subsets. So P is the counting measure. Then these are kind of trivial properties. And I'll leave, the details as an exercise. So exercise. Prove the above properties. Well, we already proved some of them. Maybe the last one needs some explanation, but it is also clear from, I guess, induction. Okay. Monotone, sequential continuity. Okay. Let AN be a countable family, be a monotone sequence in A. So it is either increasing or decreasing, okay? Then the conclusion is that limit of the probability of AN is the uh, probability of the limit. Okay, here you take limit of the sequence and then take its probability, and here we have the reverse operation. First I take the probability and then take the limit of the real numbers. Okay, so let's see the proof. First of all, okay, I will take either, since it's monotone, an increasing or decreasing sequence. Let's say first, let's take an uh, a non-decreasing sequence. So, uh, meaning that A1 is contained in A2, A2 is contained in A3, and so on. Then, of course, what is the limit of this? Limit an, in this case, is defined to be the union of the elements of the sets or sequence, elements of the sequence. Okay, note that I can write this as follows. Limit an, which is the union of an's, and this can be written like this. Another sum, ak minus ak minus 1, where a0, so when k equals 1, I have ak minus 1, so I have to define what is a0. A0 is by definition the empty set. Okay, and okay, and bk, I define it as ak minus 1. Okay, for k equals 1, 2, 3, and so on, is a pairwise disjoint sequence of events. Yani bunlar iç içe. Nedir bu? Note that this is something like this. B1 is by definition A1 minus A0. A0 is just the empty set. So B1 and A1 are the same. Suppose it is this one. And then I have B2, which is A2 minus A1. So A1 is the set inside here. A2 is the bigger one. B2 is the difference between the two. A3 is this. This is A3. So B3 is just A3 minus A2. Okay. So these are just this, circular regions, and they are all disjoint. Since they are disjoint, their measures adds up, right? So this implies that measure of this union k from 1 to infinity, a case, this thing is just the okay, measure of b case. Oops. Değil mi? Because union of a n's or a case is the same as union of b case, right? Ak minus 1 is bk. So these two unions are the same. However, the second union is a union of disjoint sets. Okay, that's the advantage. And since they are disjoint, I can write the measure of this as the sum of these gadgets. Okay, and what is this? Well, I can write this as follows. This is limit, right? This is an infinite sequence, series. How do we define this? Well, we define it this way. Limit as n goes to infinity, k from 1 to n, mu bk. Değil mi? The sum of an infinite series is defined as the limit of the partial sums. Okay. And what is this? Well, this is limit as n goes to infinity. So you see I have here mu of b1 plus mu of bn, right? But b1 to bn are disjoint. Therefore, this summation is equal to, again, the measure of the union, because bi's are disjoint. Since bi's are disjoint. And what is the sum of, what is the union of b1 to bn? That is, of course, the sum nedir? Bunlar b1'den n'e kadar. B1 is this, B2 is this. So the union of B1 and B2 is A2. The union of B1, B2, B3 is A3. So the union of B1 up to Bn will be just An. Okay. So this thing is just mu of An. And we are done. Okay. Değil mi? Göstermek istediğimiz şey zaten oydu. We want to prove that limit of the measure of the limit of ANs is the limit of the measures. Biz ne göstermiş olduk? So we show the following. Okay, we showed that measure of the union, so limit. So measure of the limit of AN, right? That's equal to the union. And we showed that this is just the limit of the real numbers, mu ans. What about decreasing sequences, non-increasing sequences? There you have to take complements. Okay, I'll leave the non-increasing case as an exercise. Yani şey alırsanız, so you take sequence, but this time you have this. But we proved the other direction. So just take the complements. Okay, when you take the complements, you will have this, and apply the previous, what we have proved to this one. And keep in mind that a set and its complement have measures, right? So that if one of them is, let's say, PA, the other one is 1 minus PA. So kitapta var zaten de hani düşünmek için size bırakayım. Okay. Corollary, şöyle bir corollary'si var. So we have a corollary sigma sub additivity. Additivity. Let AI, I in I, be any countable family of events in A, not necessarily an increasing sequence or decreasing sequence, okay? Just any family of countable events, then the probability of the union is less than the sum of the probabilities. Peki bunun ispatı, what about the proof? Well, since we take countable families, so we may just take the index set to be the set of integers, okay? Okay, then this union is just the union of ANs, let's say. Let Bn to be the union of the first n of them, okay? For any n in n. O zaman bu bir monoton sequence. Then Bn is a monotone sequence. Right? This is an increasing sequence. B1 is contained in B2, B2 is contained in B3, and so on. Right? Bn is contained in Bn plus 1 for all n. And by the previous result, now by the previous result, okay. Yeah. Şimdi şuna bakalım. Bunların union'ı this infinite union is the union of the partial şöyle yazayım. By the previous result applied to, şöyle diyeyim. Şimdi limit bn'i şöyle yazayım. Since this is a monotone sequence, its union, its limit is the union. But what is bn? Bn is just partial sums of a case. So union of the partial sums is of course just the union. So these two unions are the same. In other words, we wrote this union of arbitrary sets as the union of a monotone sequence. Okay, that's the advantage. And once we do this, of course, I can use the previous result. So we apply the previous result to this and obtain, ne elde edeceğiz? P of the union of ANs. Well, this union is this union, so this is the same thing as the probability of BNs. But this is a monotone sequence, therefore, okay, this union is just the limit of BNs, and I can take limit outside. This is what we have just proved. And okay, so we have this, and finally, hence this gadget, which is just limit of P of A1 up to AN, right? Uh, efendim? Bunu böyle yazdığı zaman şunu niye yaptık ki o zaman diye düşünüyorum da. Limit Bn şöyle yazmamız daha iyi değil mi? Bn dediğimiz şeyde Bn is what? Bn is just A1 union AN, right? And this thing is just less than sum of PIs, right? Because the if they were disjoint, then they would be the same. In general, they are not disjoint. So I have this I from, sorry, I from 1 to n, and here I take limit. And what is this? This is, of course, the definition of this infinite sequence, right? This is just n from 1 to infinity p of an. Ya da I diye de yazabiliriz ama fark etmez. Evet. Yine zamanı bitirmişim. Okay. Do you have any questions?